to day 3 of our workshop. Thank you, and we're thrilled to have Nika Haghtalab here from UC Berkeley, who works in algorithms and machine learning. And today she's going to be talking about learning with adaptive, smooth adversaries. So take it away.
Thank you for the invitation, and thank you all for being here. Yeah, the title of the talk, as you can see, is Learning with Adaptive Smooth Adversaries, and we're going to really be exploring a perspective of smooth analysis on machine learning. This is a joint work with Tim Roughgarden, who I'm sure you all know and have met, and Abhishek Shetty, who is my PhD student. Abhishek is actually present in the room, so if you need help recognizing him, this is his mask face. Yeah, so he's around a lot in Simons, and you can definitely talk with him, and you're gonna get to know about all of his other amazing works as well. So we're going to be talking about ML algorithmic and statistical guarantees in this talk. And they're usually considered in 2 different worlds. One that is stochastic, or sometimes we call them offline, and another which is adversarial, robust, or online world. So in the stochastic world, the assumption is that data that you're working with is stochastically generated from some fixed distribution that's unknown. The learner wants to learn a function using this data, and the learner is successful if it has a good performance over this underlying distribution. And this model is not at all concerned about what happens if the world were to change tomorrow, if the distribution shifts, if I'm still going to do well or not. There's the adversarial, robust, or online setting, where the assumption is that the data is generated by an all-powerful adversary. This is an adaptive adversary who knows the world and knows the history and knows the algorithm. And our algorithm is successful if it can get good performance over any adversarially generated sequence, no matter what. And this is specifically made to have robustness as part of the guarantees, because you're robust to any misspecification, any changes in the data, any attacks by just definition. So it's not surprising that these 2 types of guarantees are actually quite different from each other. A lot of cases, we can get the type of guarantees in the stochastic world that we want, quite easily with very little data or very little computation. But once you start thinking about the adversarial world, you actually have impossibility results that say that you cannot learn at all, no matter how much data or how much time you have. And this is the unfortunate thing, because we really do care about robustness. And in particular, I think more and more these days, we care about robustness more because we are seeing increased interactions between learning algorithms and people. And these types of interactions are unpredictable. They can switch based on time and shift the distribution. And robustness is really important to actually make sure that these algorithms are going to continue performing well in presence of people. And here, kind of like the impossibility results for not being able to deal with a worst case all-powerful adversary does not actually discourage us or invalidate like the actual goal of wanting to be robust. Rather, what it tells us is that we need to think about new models that can actually guide the design of algorithms that can be robust, if not to worst case all-powerful adversaries, to at least everyday type of adversaries that we are going to see. And our goal and hope is that by finding the right models and that provide the right guidance to us, we can essentially get the same performance guarantees that we could get in the stochastic world, and now get it for all sort of day-to-day type of realistic adversaries we're going to face. This is the overall view of what you're going to do today. It's of course not new. This is something that we've been doing in just algorithm design as well. It's not just about learning theory. In algorithm design, the 2 fields of average case analysis and worst case analysis exactly look at, for average case, like how can we deal with instances that were stochastically generated from a fixed distribution. And in the worst case setting, we want to analyze what happens to algorithms if instances were generated by an adversary. And also in the algorithms world, we've seen that one average case analysis could be much, much easier than worst case analysis. So looking at the algorithmic world, the solution to sort of interpolates between average case analysis and worst case analysis, the main framework that we use is smooth analysis. Many of you are familiar with this. This is a smooth analysis framework of Spielman and Teng, which essentially the idea there is that you have an adversary that chooses an instance, but then the nature comes in and perturbs this instance a little bit, perhaps by adding a Gaussian noise to it. And the goal of analysis here is that for any adversarially generated instance, we can perform well in expectation or with high probability over this noise. There's a slightly more modern perspective on thinking about how we would frame smooth analysis. And in this setting, rather than thinking that an adversary first comes and then the nature comes in, we just think that the adversary is selecting a distribution where the instances are going to be generated from this distribution. And this distribution should not be too concentrated on any one instance. So it's dispersed and anti-concentrated. And the goal there is that for any anti-concentrated, sufficiently anti-concentrated distribution, we want our algorithms to perform well, again, either in expectation or with high probability. This type of smooth analysis framework is most useful, first of all, when you have a big gap between the average case and worst case analysis, because it's really trying to go in between them. And especially useful when we see really good performance in average case, but the reason worst case analysis is not doing very well is that there were these really brittle constructions that once you add a little bit of noise, they start breaking down. Ideally, what we really want is that we are looking at smooth analysis. We can get average case analysis type guarantees for a world that is essentially worst case plus a noise. Smooth analysis, of course, has a glorious past and present and hopefully future. It was originally introduced and for the setting of thinking about how simplex does. Particularly simplex, as we know, simplex does poorly on worst case generated instances. It can have an exponential runtime, but when you add a little bit of perturbations, it actually finds a good solution within quite a small polynomial time. It has also been used for other algorithmic problems like clustering or TSP. But what I'm hoping to do today is to convince you that machine learning is also, and theory of machine learning is also should be one of the main applications of smooth analysis. And I think it should perform a fundamental role in the type of problems we study. And here, not only we care about computation, but in fact, we care even more so about information, because even definition of what is learnable depends on how much information and how much like statistical information we need. And this is also something that the model of the adversary or the stochastic world are going to impact. Okay, so I've been talking about worst case learning, stochastic learning. Let me start by actually giving you some frameworks that we can continue using throughout the talk. For today's talk, when I talk about this kind of a adversarial learning, I really mean online adversarial full information. So what does that look like? An example of this is that we have an unknown threshold A. Any instance X that we get above A is going to be labeled positive. Any instance below it is going to be labeled negative. And we want an algorithm that can predict the label of the next incoming instance. And these instances are chosen adaptively and adversarially. So in this case, let's look at a bad example and essentially prove why it's impossible to learn effectively in the online setting. Think about an adversary that asks you to label 1/2. You can say plus or minus, it really doesn't matter. But whatever you say, let's say that algorithm predicted that the label of this thing was minus. The adversary can pretend that the algorithm made a mistake and say that actually, no, the label was +1. And it can then continue asking a question without really shrinking the space of all available thresholds that would be still in the running. So then it asks for 1/4. Again, it really doesn't matter what the algorithm says. The adversary can pretend that the algorithm was wrong and continue this way. This construction, the important thing about this construction is that when I quit, in fact, I don't need to quit. I can take this to infinity. there is still one threshold, A, that was consistent with all the things the adversary said. So if I look back at my sequence, there is a perfect threshold that explains everything. And it can explain it for any route that the algorithm and adversary took. But what happened was that the algorithm had no idea. Whatever it did, it essentially ended up being a mistake. So in this case, the algorithm over t times steps is making a number of mistakes. That's exactly t. So we say that the algorithm is not learning because it's, it just makes a mistake at every round. So this is an impossibility of one example of impossibility in learning in an online setting. What would have the offline world look like? The offline world, the sequence is not adversarial anymore. It just comes from one distribution. I still have the same rule about there is a threshold that is consistent with the pluses and minuses. It's just that the instances, the x's are generated at random. Yeah.
What the distribution is.
No, the learner does not know a given distribution. So this distribution is unknown and still wants to learn this A. So why can you actually learn in this setting? There is a simple setting, like simple way to think about it. Let's say that this is a distribution and I don't really know the distribution, but there exists one. And this would have been my perfect A. So let's take the following naive algorithm, which wastes its first square root of t time by just doing arbitrary stuff. It really doesn't care. It just wants to do something to get an observation. And within this like 1/epsilon rounds, it's going to predict, this should have been reverse. It's going to predict however it wants, and it's going to make mistakes that are like at every round. So square root of t mistakes. Then what it's going to do is that it's going to look back at these square root of t rounds, and it's going to take just one threshold that looked consistent with the history. That's the A bar. This is ERM, okay? And what that happens is that it's going to just put some A bar that's consistent. And from then on up to the rest of the time, it's going to use A bar to predict. Now, why is this a good algorithm? The claim is that, first of all, the number of mistakes you made here wasn't a lot. It's sublinear in t. So compared to making t mistakes over t time steps, it's not a big deal at all. What about the mistakes you make in the future? It shouldn't be hard to see that this A bar is converging to A quite fast. And the reason for this is that essentially after square root of t rounds, if I look at any interval of length epsilon around A, I would have seen with high probability some sample falling in that region. And because it fell in that region, my A bar would have been inconsistent with it. So the fact that A bar is itself consistent is the thing that is telling me that the number of mistakes I'll make from now until future is going to be bounded and small. Okay, so this is a very naive algorithm and naive proof of what the difference between the online setting and the offline setting looks like. And it's something that typically you might learn this in the first graduate learning theory course. Okay, let me give you a formal setup of what, generally speaking, for any function class, offline and online learning are defined as. So the offline learning setting, so this is the stochastic world, you have an unknown distribution D over X, Y. Y's are the labels, X's are the instances, and you have a function class H. At every round T, you're taking this, the learner has to pick a function FT, which is not necessarily, like you don't need to take it deterministically. And then the world will pick XT, YT from a distribution. And the algorithm makes a mistake if it makes a mistake. Now, we want to get sublinear in T regret, and regret is really defined as the difference between the algorithm's number of mistakes versus the number of mistakes that the best classifier would have made. So when we were talking about these thresholds, A, the number of mistakes the best classifier made in my tree was 0. The number of mistakes the algorithm made was T. So I did not have a no regret algorithm then. But in the offline setting, the number of mistakes the algorithm made was root T. The number of mistakes that the best hypothesis made was 0. So it was a no regret algorithm. The reason we are interested in no regret is that as t goes to infinity, essentially the average regret, which is the average extra number of mistakes you're making, is going to go to 0, and it's going to be no worse than the best predictor. Okay, so that's the formal setup of offline learning. What happens to online learning? Online learning, we don't have a distribution. This is where the adversary inserting itself. So at every round, the adversary is picking x, t, y, t, having known all of the history and the algorithm at play. The middle ground smooth analysis here is going to look like how we are going to introduce some noise to the adversary. I'll say it in 2 different ways. You can think about having a function class, h, the same function class. We're just like working exactly with the same setup. And we're still working with a setup that the predictor, the learner has to pick a predictor, and the adversary is creating an instance. But how the adversaries create an instance is by picking a sigma smooth distribution, dt, having known the history so far in the algorithm. What is the sigma smooth? If you recall, I was talking about smooth analysis earlier on as picking an anti-concentrated distribution. That's what a sigma smooth distribution is. A sigma smooth distribution is one that its max density is not much larger than the uniform density. So it's like 1 over sigma times the uniform density. And if you wanted to like think more about sort of the more classical perspective on smooth analysis, another way to think about this is that, again, the adversary picked an x, t, y, t, and we randomly perturbed it. These are essentially equivalent up to some parameters, as long as you have a finite Libé measure on the domain that you're working with, which we're just going to use that as an assumption. Okay, so we talked about offline learning, online learning, and smooth perspective on online learning. What we do know about these cases are that if you're just like thinking about worst case, online learning is known to be much worse than offline learning. In fact, there's a combinatorial dimension called the Littlestone dimension that characterizes the regret in the online setting. VC dimension characterizes regret in the offline setting. And we know that Littlestone dimension is much, much larger than VC dimension. In the threshold case, VC dimension is 1, Littlestone dimension is infinite. For the purpose of this talk, you don't actually need to know what Littlestone dimension is. We don't care about it. What you would benefit from is knowing that Littlestone dimension is always less than log of h. So if you had a finite class, you could have learned. It's really the infinite classes that are creating problems for us. Now, what we're going to show you is that when you are thinking about smooth adversaries, the regret effectively is going to look like offline setting in the sense that it's still characterized by the VC dimension. But of course, it's going to have some dependence on the amount of perturbation. The more perturbation you have, the closer it's going to look like the regret in the offline setting. If you have no perturbation, it's going to go back to the Littlestone dimension. Yes?
Sigma as sort of a noise parameter. Does something have to do with like a signal to noise ratio in terms of this?
You could think about signal to noise. Instead of thinking about signal to noise, I think it's better to think about the domain size to noise. I think that is a better intuition to have here. Of course, these are related to each other. Yes.
For online learning of thresholds, just remind me, I mean, the Littlestone dimension is infinity, but if I have a bound on the range in which my threshold lies of size t, then it's logarithmic in t. I can call it t, right?
No, so t is the number of time steps.
Sorry, not t. I mean
h.
If I don't know, call it m or something. If I know that my threshold lies in a bound somewhere between minus m and m.
Unfortunately, not. So even if you put it, it's kind of scale free, unfortunately, and that's the issue. If you have a discretized set that I say it lies between 1, 2, 3 to m, all integers, then yes, because you have m options and then you can use this. But if it's just lying between 0 to 1, it's somewhat scale free because when I'm doing that half, what happens, let me see.
Problem is too many real numbers.
Yeah, it's exactly.
Right, so I mean, what if there, like, how does this square with, I mean, there are like classical results that in the mistake bounded setting that you can learn linear threshold functions.
only if there are finitely many of them. There's always an asterisk.
Okay, so if there's some bounded precision.
Bounded precision, you're okay, exactly. So this is exactly the issue. If you have, if I discretize this so that I have 2 to the some number of them, then you're going to get a regret that's going to be square root of t. Like, let's say I have n, like 2 to the n here, then you're going to get square root of tn. As n goes to infinity, you don't have a discretization. This is going to go to not being able to learn. Yeah, it's interesting because we do think about these, we teach them differently than they're actually used. And in fact, this Littleson dimension, whenever you have a threshold in your class, essentially Littleson dimension is infinite. Yes?
Does the adversary has a noise, particular noise model, or is it like arbitrary?
No. So when we think about the sigma smooth, that's just so that we don't have to think about noise models at all. So sigma smooth just means that you can pick any distribution correlated with the past, as in your choice of distribution is correlated with the past, but it cannot have infinitely large density. Okay, so this is what we've seen. This is what we're going to do. Any questions? Any other questions? You had good questions. Okay, so yeah, one thing I was talking about learnability is that we talk about, like, the reason we like to think about no regret is that we define learnability in that sense. So you're learnable, the class is learnable if you can get sublinear anti-regret. So this is actually changing our perspective of what is learnable. Previously, we thought that, you know, classifiers with large Littleson dimension were not learnable in the adversarial setting. What this is really telling us is that actually they are learnable in the smoothed version of the problem. So just changing the characterization entirely. Yeah.
So in one sense, the smooth analysis setup is not exactly an interpolation between the two, because in the pure stochastic setting, you don't need the, you know, like there's only one distribution for all time, and it need not be sigma smooth. But here you're allowing different distributions in every time, but each one has to be sigma.
Yeah, it's actually, this is something that's that's more interesting as a difference between more algorithmic way of thinking and more ML theoretic way of thinking, which is that when we talk about average case analysis, and if here also when I take sigma to be 1, I am essentially talking about uniformity. Whereas the offline setting actually works for any distribution, not any fixed distribution. Yes, there's a little bit of dissonance here. I completely agree with you. It happens to be, so when I talk about this being a characterization, I'm just hiding some stuff that I will be happy to reveal offline in the talk, not offline online after the talk. But yeah, it's a very good observation. Okay, so to see why smooth analysis helps here is important to maybe take a look at the stochastic case. And actually, before I do that, let me just say that another important aspect here, I said it, but I think I should just say it one more time, is that this sigma smooth distribution, you were asking about the noise model. It's really important that you have the knowledge of the history of the past, right? So it's not that I just, at the beginning, I picked the sequence of like anti-concentrated distributions. It's really that the adversary is still quite adversarial and adapted. It can adapt to the past. And this is the thing we're trying to really deal with, because if the adversary wasn't very adaptive, we would be back in the typical way of looking at smooth analysis. The adaptivity here is actually a significant challenge. Okay, so why did the stochastic setting work? At a high level, one explanation for this is that even when you have an infinite hypothesis class, you can take a finite net of this, a finite cover for it, and then just pretend that you were in the world where you only needed to work with a finite case. So what this looks like is that we can have this net. The net here is defined as for every function in my original function class, there is this proxy in my smaller net where really in expectations, these are very close to each other. An expectation taken over the distribution that we don't know, but there exists such a net, and the net is small. And this net in the example I gave you essentially look like the epsilon intervals that I could have essentially written these epsilon intervals, only picked these hypotheses that are at the corners of these epsilons, and anything that falls in the interval next to it is going to be mapped to its proxy, which is at that discretization level. The discretization, of course, has to depend on the distribution. So, but once you have such a just existence of such a net, all you need to do is say that this net is really good. Not many instances can fall between any of these grids because there was very little probability there to start with. And there are infinitely many these little epsilon kind of intervals, but they happen to be very structured. In particular, in this case, they have a very good VC dimension. And because of that, we can take union bound over infinitely many of them. So this is just an alternative explanation of why we can learn in the offline setting. And really, it's about this anti-concentration of what happens in this error of the net. Now, the challenge here is that we cannot really use this because when we have an adversary, the adversary can exactly focus on any fixed net and try to make the error very high in that area. And that's the issue. So what we are going to see is that we can preserve some of this anti-concentratedness of a smooth sequence, because at any given time, that adversary who had to be sigma smooth cannot focus too much on any of these intervals. And the hope should be that even by correlating across the history, he still has very limited power of focusing on any one interval. And that's what we are going to see. Of course, the challenge here is that exactly these correlations, because you might worry that maybe at this time, it cannot focus too much, but T is quite large. And maybe with sufficient patience, it can start focusing on some interval that I wasn't thinking about. Okay, so how we're going to deal with this challenge is that we're actually going to try to connect anything that a smooth adversary can do to anything that a uniform adversary could have done. What does this look like? It says that I don't have to worry at all about any of these adaptiveness of an adversary. What I do need to do is to sort of understand if the sequence that can be created by an adversary looks like a sequence that could have been created by uniform distribution. And we do this via probability coupling. Probability coupling at a high level is just a joint distribution between these two processes. And it's a joint distribution that has some nice property. So I can look at anything in its support, and I can sort of compare something on the two sides of the two distributions. And our goal is going to be to couple a sequence of smooth distributions with draws from a uniform distribution. What we can show is that we have such a coupling. So our coupling theorem, which is very general, it goes beyond online learning, is that you can couple T draws from this adaptive smooth adversary with a little bit more than T over sigma, essentially, number of draws from the uniform distribution. And what is the nice property about this coupling? It's a notion of monotonicity, that with high probability, the things that the adversary would have produced were a subset of the things that would have been produced by a uniform distribution. Okay?
And subset, you mean like those are actually sets of things?
These are, yeah, take a set. Yeah, yeah. Curly braces are missing, sorry. And not ordered. The order doesn't matter. Okay, so why is this a good property to have? Essentially, we know and agree that uniform distribution is not concentrated. It's like the least concentrated distribution you can think about. And if the things that the adversary is creating is going to be somewhat a subset of this, it's also not going to be concentrated. as long as I scale what I mean by concentrated by this 1/sigma. In other words, I kind of want to say that that approximation error of the net was small, which is this the symmetric difference between any hypothesis and its proxy. And I know it's going to be small over the uniform distribution. And if it's small over the uniform distribution, and uniform distribution is going to be sort of overtaking whatever the adversary is doing, then also the adversary cannot produce too many samples in that region. And because of that, the adversary cannot focus on any of those small epsilon intervals that I was worried about. So that's the main very powerful but simple tool that we have that essentially tells us that adaptive adversaries cannot be much worse than a stochastic adversary on a slightly different time scale. The t itself is the time scale that's changing. Okay, so with that in mind, how are we going to really use this tool as a pretty powerful weapon? We are going to think about this as just repeating the stochastic analysis back with slight changes. So we start by taking a finite approximation over our hypothesis class. Which finite approximation are we going to take? We don't have a distribution anymore. It's an adversarial world. What we're going to do is that we're going to take one with respect to the uniform distribution. Why uniform? Kind of makes sense. You know, our sigma smooth distributions are worst case scalings of these uniform distributions. So if you can do something in expectation that looks good for the uniform for one round without any correlation, it doesn't look that bad for a sigma smooth distribution. Once we have this net, what are we going to do with this net? Well, algorithmically, and this is an algorithm, not a computationally efficient one, but an algorithm. I'm just going to take this net and I'm just going to pretend that this was my class. And I'm going to then have a regret that is scaling logarithmic with this size of the H prime. It turns out that these nets, we do know that they're not that large. In particular, even you can think about this as just taking a slightly tighter net on a uniform distribution. And they happen to only have dependencies on, the log of them happens to have dependencies that is linear on in BC dimension. So that's okay. So this is the first step. We take the net. Once we have the net, we know that in expectation, no round can put too high of a probability of anything falling in the error range, the approximation error. Then what we do is that we're going to apply the coupling. Here, the coupling says that, yeah, we are dealing with the adaptive adversary and our net was for the uniform distribution. Approximation error, which is really thinking about in expectation over all of these correlated things and what happens to the max, is going to still be bounded by this monotonicity, the nice property of the coupling that we had. So this is going to allow us to really take the fact that, you know, the things that the adversary generated was a subset of the things that the uniform distribution would have generated, to just say that we are back in the uniform world. Once we are back in the uniform world, then we can just bound the approximation error based on the uniform distribution. This is where, again, the typical BC theory magic comes in. There is nothing about adaptivity. It's just offline learning. Whatever you were doing with offline learning and BC dimension or coverage number, they come in here. So that's it. This coupling method allowed us to really go back from an adaptive adversary to the uniform world, to the average analysis world. And we wanted to be robust to T interactions with an adaptive smooth adversary. And what we saw was that classical algorithms and analysis could have been lifted and used essentially directly in the smoothed adaptive world. So I told you the story about online learning, but really this story is bigger than online learning. That was just one clean example. This is true for any other adaptive online process and decision problem we have. And our goals are the same, which was that we want to essentially get as best performance as we can in the offline world, but in the online world. And what smooth analysis is saying is that you can get rid of the worst part of an adversary by using this coupling, by essentially reducing interactions with an adaptive adversary to what would have happened in the average case analysis with a uniform distribution. A general recipe of how you would think about applying this, since we've applied to a bunch of other problems, is that you just solve the problem for the uniform case, and then go back and identify the steps that anti-concentration was used. If worst case is much worse than average case, it's because anti-concentration was used somewhere in the analysis of the average case setting. Once you identify them, you'll notice that they all actually have this type of a constant monotonicity properties, either a potential function, sometimes it's, as you saw, it was actually a coverage function. All of these benefit from anti-concentration, and all of them can be replaced with this coupling lemma to just work with an adaptive adversary rather than a uniform one. And then you just replace whatever the coupling lemma tells you, and you're back in the world where the original problem held for the uniform distribution. We have repeated, just telling you very quickly, what we have done is that this problem we've also applied to online discrepancy minimization. If you're not familiar with this, you can think about this as having a bunch of vectors that come one at a time, and they're in an L2 bound. You have to give plus and minuses to them, like cluster them in two settings. And you want these to look as close as possible to each other. So the positive and the negative set, then you just take an average over them. The vector is as short as possible. And we know that in the worst case, you cannot do better than square root of t, essentially because always the adversary can give you something that's not correlated, that's orthogonal to the past. And there are recent results in the average case setting, either for uniform distribution or fixed distributions or oblivious adversaries, that say that you can get this poly-NT type result. What we can show is that you can get that polylog NT result even for smooth adaptive adversaries, again, using this type of a coupling. So again, you can take the worst aspect of an adversary out and get results that you could have gotten for a fixed distribution. Okay, that's that. I just wanted to say that I gave you one example in detail, one example pretty rushed, but this is a bigger trend. And this coupling lemma itself was very simple, but powerful in trying to bring the typical offline analysis to an adaptive, smooth analysis. We focus mostly on the information theoretic aspects of learning, but the computational aspects are just as important. And there's not a lot of work. In particular, one open problem here is that for the online learning world that I gave you, is there any computationally efficient algorithm that rather than the algorithm that's running on the net? So that's one major open problem in this space. More generally, I just hope that you take away from this talk that the existing frameworks of beyond worst case analysis that are used for algorithmic analysis have both very interesting and challenging open problems when it comes to learning, and also can bring a unique perspective on learning, because it's not just that the computation is the thing that you're trying to limit, but they're actually changing the characterization of learnability even to start with. With that, thank you. I will take questions.
Do you have any idea whether the uniform distribution is sort of the best and only distribution that you should use?
You mean in terms of defining smooth analysis at 1/sigma? No, it's not the only, but we also don't think we can define it based on any distribution. There are some regularity assumptions.
Okay. Do you know of some case where like the uniform distribution doesn't give you what you want, but maybe some other distribution might?
We don't. We don't, because I think uniform is somewhat, to me, is somewhat actually the pessimistic. Like it's as if, hey, I don't know anything about my distribution except for the scaling. If I assume Gaussian, it's as if I know a little bit more, but it's not something we've thought about. And there's
is there an analog of this kind of result for simple multi-arm bandits?
So simple multi-arm bandits, you mean like with bandits, like actual bandits, right? We haven't worked it out, and there essentially it's not just the discretization that matters. You also care about how partial information comes in. The main challenge there is that it's not even, we don't have actual characterization of what the regret should look like for any continuous multi-arm bandit problem. It's not like we don't have VC dimension. We have some dimensions, but they are usually only bounding the regret, upper bounding it and not lower bounding it. So absent that characterization, we are a little bit in trouble making such a crisp story, but we do believe that it should help. Especially, I can tell you that one of the applications I didn't talk about today is about online optimization beyond online learning. And there, both the full information and partial information essentially use very similar type of guarantees. So I think in limited scenarios, we can definitely do that. But I think the story is not going to be quite as clean here just because the characterization is missing even for the worst case.
There is some understanding about how like certain, like for example, linear contextual bandits, like some smoothing of those concepts.
Yeah, so linear contextual bandits, there is some, yeah. So Jamie and collaborators, and also another paper from MSR with, I want to say Manish Raghavan and collaborators, have some understanding for linear bandits. But more generally, as I said, like generally, if you speak about any H, it's just we don't know even the characterization for the worst case.
I guess I have a very small question, and that is, when I think about smooth analysis in machine learning, you know, there are kind of two worlds you could live in. One is, and it makes more sense for this particular problem, you're going to smooth the distribution, but you could also consider smoothing the function class.
Yeah.
Is there some, you know, smoothed function class that you've also considered here? Or?
Yeah, so you could smooth the function class, and things usually become much easier. So one thing that is the real challenge here is the correlatedness across. And the fact that you're still keeping the little Sun dimension at infinity, and you're creating these correlated but smooth distributions. When you create a smoothed function itself, you're actually changing its own like sequential random marker complexity by adding some Lipschitzness to it. So results, first of all, become much simpler to deal with, but also a little bit less robust to thinking about the scale of noise, the meaning of the scale of the noise, just because these noises could sort of build up, and those noises don't build up just because the function class itself, the Lipschitzness value of it was fixed.
Although, as you say, the noises don't.
They don't, yeah. So you have to prove that they don't. In some cases, they could, right? In these applications, they don't. But yeah, so I guess long story short, you could think about just looking at sequential random marker complexity of a function class, and the function class itself being a bit more smoothed. I believe there was a older paper. I'm worried that I might not actually be citing the authors, but I think it's Shai Ben David and Shai Shalom Schwartz, and perhaps one other author that looks at this kind of agnostic learning when you're making these thresholds to be a little bit more Lipschitz. So, yeah, so that is also very interesting and something that people have thought about a little bit.
Okay, let's thank Nika again. That was a good.